Right, so let's get started with the third part of our class this week, in which we're going to look into the geometry of linear programs. The idea is to give a graphical interpretation of the geometry of LPs, of linear programs, and then we'll use that to understand and try to visualize what are the key features that LPs have that can be exploited by a efficient solution method. So let's go back to that problem we just modeled, is the paint production problem. Like we had before, so this is our objective function, and we have this set of 4 constraints, which we saw that we can represent compactly in this form. So if you remember, the matrix A here represents this 6, 1, minus 1, 0, and then 4, 2, 1, and 1. Let me put a bit better line here. 1 and 1. There you go. Right, and we have our vector B. Let me move it a bit further down. And our vector B, which is represented by 24, 6, 1, and 2. Right? So you can see that this A matrix is M by N, in the sense that I have M constraints, in this case 4, and N decision variables, in this case 2. And this is a component-wise requirement that those are all non-negative. Okay, and B then has a dimension M, and C has a dimension N. I'm insisting on these details now because what coming next week and in the next classes, this is kind of like a standard notation that we're going to use in terms of sizes. So it's good that you kind of start to get familiar with how big these elements are when we're using this a more algebraic notation. All right, so one thing to notice is that if you think of the rows of your matrix A, each of these constraints are defined by this row, by one row that forms one inequality, like so. So for example, this, if I go back here, so my matrix A, for the first line, I have 6 and 4 here, and that first line is forming exactly this constraint there, which is what I'm denoting here. So lowercase I AI represents one of the rows of that matrix, which are then, have one constraint here. And as you might know, every inequality forms what is called a closed half space, which in this case has the boundary defined by the hyperplane on the equality. So it means that the boundary of this half space is given by that, that equation there, which is representing the boundary of this this closed half space. So if each of those form a closed half space, it means that a feasible solution for this problem, a solution that satisfies this point, this constraint, this constraint, this constraint, and this constraint. So it has to be a point that is the intersection of the closed half spaces that are formed by each of these constraints. Let's have a look at this concept. We're going to go back to this notion of hyperplane, half spaces in a more non-formal setting, but for now, I'm just giving you a collection of information that is basically the central aspects that we're going to exploit when we develop the actual optimization method that we're going to apply to linear programs. But let's have a look at this visually to see some of the important consequences of the geometry of this. So this first constraint there is this. So 6x1 plus 4x2 less or equal than 24. It was the requirement for M1, for resource M1. And if you look that into a two-dimensional space where each coordinate is represented by my decision variables, you can plot this boundary by plotting the equation 6x1 plus 4x2 equals 24, right? So the way to plot this, I don't know if you remember, but it's simply you get 2 points, so you can assemble a table like so. So if, say, x1 is 4, and then you replace 4 here, you mean that x2 is 0, And if you look at the point where x1 is 0, then you obtain that x2 is 6, because it's 24 divided by 4. And with these 2 points, 4, 0, and 0, 6, you have 2 points. Then you can draw a straight line, and that would be the boundary. But because we are the closed half space, we want everything that is less or equal than 24. So half spaces, they are either on one side or the other. They divide the space into 2 spaces. So your in our case here, R2 would divide it in 2 half spaces. That's why it's called half space. And now to know whether I'm talking about this side or that side, just pick a point. You can pick 1, 1, substitute here. You see that 1 and 1 are going to give you 10, which is less than 24. So everyone else on this side has to be less than 24. One easy point to test is always 0, 0. The origin is a good point to test. So if you put your origin here, you see that this is 0, 0 is less than 24. So all the neighboring points to the origin also has to be less than 24. So this is how we draw constraints and define what's the closed half space we're talking about. Well, with that then done, we can do the second constraint, which looked like so. So x1 plus 2x2 less or equal than 6. I do the same trick to get 0, 6, 6, 0, and 0, 3. Draw the line. And now you can see that the region that represents the intersection between these two constraints is this one here, right? So these points are the points that satisfy simultaneously this constraint and this constraint. So they are, because they are the intersection between the closed half spaces, right? We have a third constraint, that constraint relating to the maximum production capacity. So I said that I didn't want to have x2 to be greater than 1 plus x1. And that gives us a very different constraint because of this negative coefficient there. But the logic is exactly the same. You get 2 points. You can't rely on a point crossing the axis x1, or you can, but you will have to have the extension on the negative side. So then you will have this straight line there. And 0, 0 is less or equal than 1, so the origin is in the half space defined of interest for us in this constraint. And you can see that it cuts out this part. So our new feasible region is this sort of figure that is forming here, that is looking like a polyhedral set, a polyhedron. By the way, we are only looking into the positive orthant because we have the constraint that x1 and x2 is greater than or equal than 0. So we already there is a constraint saying that we only want x2 to be in this realm and x1 to be in that. Okay. So with that all, there's this last constraint saying that the maximum demand of x2 was 2. So we have also this last constraint here. And now the intersection of the 4 forms this polyhedral set here, which is our feasible set. So we can write here that this is our feasible set or feasible region, like so. So given a bit terminology that we're going to be using throughout the course. All right. So that's it. So basically any point within this region is going to be a point that satisfy a point x1, x2 that satisfy all my constraints, and therefore is a feasible solution, is a feasible plan. I just have now to find within among these all possible plans, what is the one that optimizes our objective function, which was maximizing our profits. And you can see that I still have a selection of infinite possibilities, right? But if we stare long enough into this picture and take into account our objective function, we start to notice something very peculiar about finding what would be the optimal production plan for this problem. And this is related with the fact that our objective function was given by something that looks like so, which in our case was 5x1 plus 4x2. So the gradient of z is in x is actually this vector c, meaning that if I want to increase z, what I have to do is simply walk in the direction of c. And c, because it's a linear problem, it turns out that this thing is constant throughout the region I'm interested in. So basically what I do is, if I look at any point, So this is gonna notice that this is forming a hyperplane in this x1 x2 space. So if I had a z axis coming out of the screen, what we'll see is something that is 0 here, and it's going up. It has an inclination that is going up as we move away from this in the direction of the gradient, right? So I can see level curves of this inclined hyperplane. So for example, I want to see what is the level curve at this direction here. So I pick a z. In this case, I picked z equals 5, because z equals 5, I know when x2 is 0, that level curve is going to cross x1 and 1, and it's going to cross x2. Well, you'll have to do some, it's 5/4 this point here, right? Because I'm looking at the equation for z equals 5. What I have is that my level curve is defined by this hyperplane, and then I do the same trick I did before to get 2 points for that. So I get 1 and 5/4, and that gives me this hyperplane here, because this gives me a direction where I should be, where things start to be interesting, because what we actually seeing is the following. As I move in the direction of my gradient, which is simply c, I know that this is going to be increasing. So when I move in this direction, I go from having a level curve of 5 to having a level curve of 10. And because I want to maximize my profit, what I'm interested in are in the points x1, x2 that are below the furthest away level curve of this hyperplane, right? Because I want to maximize. I want to find, so when I'm here, every production plan that is below this curve gives me a profit of 5. When I move this to this point, every profit gives me a production plan. Every production plan gives me a profit of 10. So if I want to maximize, I'm looking to those production plans where I can take this as further out as possible. And you can see what is going to happen when I start to push this further out. Basically, I cannot go all the way to infinite and have an infinite profit, because I am constrained to be within my my feasibility set. So the furthest away I can go in this story is actually when I get stuck to this very point right there. So you can see that this causes a sort of the geometry causes an effect that whenever I'm looking into these maximizing solutions, they always are going to end up at the outer skirt of my polyhedral feasibility set. In specific, most of the cases it's going to end up being on a vertex of it. Unless, we are sort of unfortunate enough that this orange curve is parallel to one of the facets. So it means that it's going to sit on a whole facet itself, which is kind of not the case here. But if suppose, let me get rid of this. And so if suppose my function c was such that it was exactly parallel to one of these facets, instead of being stuck to a unique vertex, it would actually be stuck to a whole facet. But not being the case, like it's here, that means that this is going to take us exactly to that point right there, which is the point where x is 3, x1 is 3, x2 is 1.5. So these are the amounts of paint I'm making. And my profit in that point is 21. And that is the maximum profit. So this process of looking at the geometry of the problem and figure out what is the optimal solution is something that is called the graphical method. And it's a simple thing that you can do with two-dimensional problems just to understand geometry. It's not properly a method, but allows us in two-dimensional problems to find optimal solutions, which in this case is exactly this one there. Okay, so let's have a look now and then on some important concepts related to how these constraints play a role in being in the optimal solution. So the first important concept is this notion of activity of constraints. So we have what we say that the constraint is active is when at the optimal value, the requirement as being satisfied at the equality of the constraint. That means that your optimal point is, or optimal vertex is lying on the boundary of that specific closed half space. So in this case, for example, in our optimal solution, these two constraints are active because our optimal solution are satisfying these requirements for M1 and M2 material for the paint. At equality. So if you substitute this optimal 0.3 and 1.5 here and here, you'll see that you get exactly 24 on this left-hand side and exactly 6 on this left-hand side. So these are active constraints, and they are active as opposed to the notion of inactive constraints, which are those that for which, when you look at the constraint, the optimal point is within the closed half space, but not at the boundary. So this is an example, the case for this green constraint here, since the difference between x1 and x2 is greater than 1, is 1.5. So it means that is within the closed half space defined by this constraint. Another inactive constraint here is this one, because x2 is strictly less than 2. So this is yet another inactive constraint. So they are not playing a role in defining the vertex that forms the optimal point. And by the way, you can see here that because this is a problem in R2, and we have originally 4 constraints, if I get any of the 4 constraints, so this and this, I form a vertex here, this and this, I form a vertex here, this one and this one actually forms the optimal vertex, so on and so forth. And even though each of them forms a vertex, which given this geometry, as we just seen, it forms our potential candidates for optimal solution, of course, some of them will not necessarily be feasible. So all of the combinations, only this one, and that one are actually feasible. By the way, this one and this one are formed with constraints that are kind of not implicitly here. In fact, we have the total of constraints in our problem is given by n plus m, because we have the m constraints that are the original problem constraints, but we have another n constraints. Remember that n is the number of variables associated with each of our variables, the non-negativity conditions of each of our variables. So x1 greater than equal than 0 and x2 greater than equal than 0 are in here. So in total, I actually have 6 of those constraints. And when I from the 6 pick 2, for example, if I look at this one here, this is the condition x2 equals 0 and 6x1 plus 4x2 equals 24. And the combination of these two constraints gives me this point. All right. And we also seen the notion of the gradient of a function, which in this case is that vector c and is constant. It gives us this sweeping direction that we move towards when we want to maximize or minimize our function. So if we're maximizing, we want to go in the direction of the gradient. So that's why we went into this direction. And if for some reason we wanted to minimize our profit, just for the sake of the example, we would have to go the other way around, which in this case, the solution that minimizes our profit is just the solution of not doing anything. So we would have this as our optimal point in case we were minimizing. But in either case, you can see that the solution is unique, or in general at least, the solution will be unique and lie on a vertex. And that means that instead of having to, look through a set of infinite possible plans, I actually have a very limited, a finite and discrete set of optimal candidates, optimal solution candidates. In this case, I have 1, 2, 3, 4, 5, and 6 to actually explore, and then just a matter of picking which one is the best. So the fact that we're now talking about a situation where we have a finite number of candidates and the set is discrete, we can use that. We'll exploit this fact in the development of an efficient solution method. So just to summarize, here is all the geometrical facts we just covered that are gonna be playing an important role in the definition of in the designing of the method we're going to be employing to find optimal solutions for all linear problems. So our feasible region is a polyhedral set. Next week we'll start giving more formal definitions of these things, what these things means. But it's a polyhedral set is a polyhedron, and it's because it's formed by closed half space, the intersection of closed half space. And because our search direction is constant, because it's the vector c that doesn't depend on the variables x, because everything the objective function is linear, we have that the number of candidate optimal solutions is finite. Typically, because you might be so that your vector c aligns with one of the facets, then you will have infinite candidates all with the same objective function. We'll also get back to this. So the candidate is typically a vertex. And vertexes are very special points because we can describe them without actually having to rely on geometry, but we can describe them relying on algebra. And the reason for that is because we can identify vertices whenever we cross n, given that I'm in Rn, whenever I cross n hyperplanes, right? The problem with that is that as I increase dimensions, number of variables and constraint, this is going to increase exponentially, and that's going to be a challenge for us. It might be so that these potential vertices or these potential candidates are just too many to be explored one by one. But we'll see that there is a justification that it won't be the case, and even though it will see that the worst case scenario, let's put it like that, for our method is that having to explore every single vertex. In practice, this is quite often, it's more than often not the case. And that method that we're going to develop is what we call the simplex method. So the simplex method is the optimization method we employ into our linear programs to find these optimal solutions. And the simplex method, what it does is just exploit these features by simply looking at combinations of n active constraints, because we know that combination of n active constraints will form as a vertex. And once I am at a given vertex, what I do is just I choose heuristically a way to replace one of these n constraints to be active from these n constraints available. So whenever I have my n constraints active and they form a vertex, what I do is, if this vertex is not satisfying an optimality condition, is not good enough, I'll take one of these n hyperplanes, remove, and pick a new one from the n other available, and see if this takes me back to somewhere else. Because that is going to mean that I'm jumping from a vertex to another, and I know that my solution is on vertices, so I just have to keep doing this switch until I find something that satisfies whatever I have in terms of optimality conditions. And this optimality condition, it's basically looking, I can predict the improvement or the deterioration I will have when I do the swap. So if I get into a situation which all possible swaps will make my current solution worse, I can stop. And I will see that we have a geometrical justification to guarantee that that solution is not only locally optimal, but globally optimal. Yeah, so this is kind of an overview of what is coming next in the next, I want to say 3 weeks. But this is kind of the plan we're now gonna, basically with this, laying out the plan of what we intend to investigate, what is coming next. So starting next week, we're gonna give a bit more formal definition of all these elements we've just seen, and how we can use these geometrical properties, how they are used to develop the simplex method, which is then what we're looking into in the following week. So that kind of lays the plan for at least a third of our course and what's coming next. So, but this is all for this week. Make sure you go through the videos and the exercise material that coming right after this as well. And I'm very much looking forward to seeing you on Thursday. Bye-bye.